We're going to finish section 2.5 out of the 301 workbook, which covers voltage and current division, by considering an interesting application and then a couple more examples of applying our VDP and CDP techniques. So one common application of voltage division, or VDP, can be found when you design position transducers. And transducers are typically used to produce voltage or current that's usually proportional to some physical or mechanical quantity of interest. For example, distance, pressure, or temperature. And below, I'm going to just draw you an illustration of a transducer that could produce an output voltage, say V0, that's proportional to a rudder angle, theta. And so the idea is that as the rudder turns, the sliding contact will move along a resistance so that a particular resistance, say R2, is proportional to the rudder angle, theta, but the total resistance remains fixed, which is sum of two resistances, R1 and R2. And so specifically from an equation standpoint, what we have is that V0 is the voltage source scaled by the scaling factor R2 over R1 plus R2, which reminds you sort of voltage division. And many times that can be represented also in this term physically as some scalar product of this rudder angle theta. And so K is some constant proportionality that will depend on the voltage source and certainly the materials used to build the transducer. So the idea is that to draw this, just a simple illustration, take a voltage source. Let's let the polarities be top positive, bottom negative. And we're going to wire that up to our rudder angle. And so we're going to make it look like this. Okay, so we're going to stop there, leave this kind of like a hole here, and draw this back around. Okay, like this. And what we're going to do is we're going to put a rudder angle in. Okay, and so the angle will be made, let's say, through this way. Okay, with the rudder here, and let's just draw it like this. Okay, so that what we do is we carve out this angle theta, and this is the rudder shaft, this long thing here. So maybe we'll illustrate that's what this is. This is the rudder shaft. Okay. And what we're doing is that the contact is made in a way so that there's voltage. So we'll kind of draw this here as an open circuit there. We'll call that the V0. This is minus plus. Okay. Right. So that's the V0 output voltage that's generated. And so the contacts are made with resistances. So kind of do the resistances are end to end. This actually would come up and make a contact with it. And there are really two of them. The first part will be R1 and the second part will be R2. And so what happens as the angle turns, we're coming into the R2 portion rather than the R1, okay? And so this illustrates that the output voltage would be a scalar form of R2 versus the total resistance given by the end-to-end resistances. So they're kind of in series, end-to-end there. And then the actual resistance that we use to scale the voltage source is given by this half of it, or this component of it, okay, all right? So you can see what happens as the angle here becomes smaller. We're carving out more R2 than we are R1, so that's sort of an illustration there. And you can adjust this according to the sizes of the resistances R1 and R2 in terms of the proportionality that you're going to get for your voltage. So that's just an interesting illustration of what VDP might exist in nature, or not nature, in terms of real examples of transducers where this mechanical positioning is actually determining the proportion of the voltage that will be generated, okay? And then you would then, you know, hook this, you would have this voltage applying perhaps to some other devices and so forth. But you are distributing this original source according to this mechanical position of that rudder, okay? All right. So let's just continue on with some examples that we're normally going to have in this class. That was just a nice little application to show you that VDP can occur in a more mechanical way. But we're going to go back and say, suppose we have a circuit. In this case, we're in series. We have 4 resistances in series, and we want to know all the label voltages. So we're going to find all 4 of these voltages. And keep in mind, in this case, we have 120 volts to distribute in the voltage source. And we know how to do this. We must get the sum. First of all, to apply VDP, we need to know what the sum is from I goes from 1 to 4, R sub I. And if we sum all the way around here, 10, added to 5, added to 15, added to 30, we know we have 60. So this is a total of 60 ohms. And then what we can do is we can get all of the individual voltages that we need by taking the corresponding resistance over that sum. So the second one would be the sum divided into the second. And then you see we're just indexing them as we go down, R4 divided by the sum, okay? And so this is VDP in action here. We know that the and this would all be multiplied times the voltage source. So let's multiply times the voltage source, okay? Times Vs, times Vs. And so we'll have 5 over 60 Vs. Here we would have 10 over 60 Vs. And here 3 would have 15 over 60 Vs. And then finally here we'd have 30 over 60 times Vs, right? And of course the voltage source is 120. So if we take 120, 60 will go in that 2 times. This would give us 10 volts. Again, this will be 120. You're going to take half of that. You're going to get 20 volts out of this. In this case, you're going to get 30 volts, correct? And last but not least, in this case, you're going to get 60 volts, okay? So again, notice how this distribution of voltage corresponds to the resistances. These are increasing as these increase, right? So you have more voltage here, 60 volts, because you have more resistance, okay? You have less voltage because you have less resistance, right? Keep in mind, how many currents are flowing through this circuit? Just one, right? Because they're in series, right? Okay, so that's VDP in action. Bottom page 44. Let's go to 45. Just one more time, just in case things don't immediately occur in series, we can still handle it. So for this particular problem, we're given that we're going to distribute 20 volts. So we know the voltage source is 20. And we want to find V1, V2, and V4. Maybe that one was V3, but we don't care. Let's just say we want to find those 3. Let's go ahead and label this resistance R1. Let's label this resistance, it doesn't really matter. Let's make the 7-1 R2. And we'll make this one R3. I guess it's kind of funky that it doesn't match up to that index, but doesn't really matter. And we'll make this one an R4, okay? So first we observe and say, well, we have these 3, are they in series? Well, no, because of this. So what we have here is we have the R2 and the R3 in parallel. So let's get a reduction there by looking at an equivalent. These 2 are in parallel, okay? So the equivalent for those 2, correct, would be R2 times R3 over their sum. And in this case, we're dealing with 7 and 5, all right? So we're gonna have 35 over this, the sum, which is 12, 35 twelfths ohms. With the calculator, that's 2.91. And the 6 repeats. So we'll leave it as 3 significant figures there. Usually, again, 3 significant figures is generally fine. right? So redrawing the voltage source here, which is 20 volts, still have this 3 ohm resistance, which is R1. We also still have this resistance down here, which is 4 ohms, and this is R4. But now we have an equivalent. We've removed the parallelism there, and we have an equivalent, correct, which is equal to 2.916 ohms, okay? Almost 3, almost the same as that, but you know, that does repeat. All right, so what advantage do we have now of finding voltages? Huge advantage, because now the problem is exactly like the previous problem. They're all in series. So now when they're all in series, you apply VDP. So that was the only point of this problem, is that you need to apply VDP. You got to make sure you got a bunch of resistances in series with the voltage source, right? So if we want to go ahead and get V2, we can get V2 by what? Well, now this is interesting because this was an equivalent for those two in parallel, but the fact that they're parallel means they share the voltage, right? So the voltage of V2 would be corresponding to the voltage through the equivalent. So we can go ahead and call that voltage V2. It'd be the same, right? Because they're in parallel. So in this case, we would use the equivalent over the sum of those resistances, which is R1 plus the REQ plus the R4, and that will be multiplied times the voltage source, right? So we would have 2.916 divided by 2.96 plus 4 plus 3, right? And that should give us 9. That's adding a total of 7 to it. So it'll give us 9.916 times the voltage source, which is 20 volts. And if you take the calculator out, that would be about 5.88 volts. And then easily do the rest of them, right? Let's go ahead and do V4. V4 would be R4 over that sum again, R1 plus the equivalent, plus R4 times Vs, and that's just 4 over that same denominator every time, times the 20 volts. That's almost 80, so it's about 8. We'd expect it close to 8.07 volts. And then finally, V1 is R1 over that sum, R1 plus the equivalent, plus R4, again, that times the voltage source. And that should be 3 over the 9.916 times the 20 volt source. And that turns out to be about a little over 6.05 volts. So there we have it. We have determined that you will have about 5.8 volts passing through both the 5 ohm and the 7 ohms, remember, because that's the voltage to the equivalent, which is an equivalent of parallel resistances. So therefore, you've got the voltage on those two. The voltage through the R4 one is the highest, it's 8. And then you have the voltage through the 3 as, through the 3 ohm, which is R1, is 6. So it's kind of interesting that the voltage is highest through the 4 ohm. You might have thought, well, wait a second, these have higher resistances, but they are in parallel, right? So they are if we think about the 20 volts, right, we have got 5, that's, that's almost 13. I mean, you can see how this is summing. These 3 are definitely summing to be close to 20 volts. So, it's interesting that even though this is a larger ohm than that, this parallelism is causing that you're getting the same voltage to occur there, right? So, and the fraction, it was based on the equivalent resistance, which is less than the 5 and the 7. See, it's less than the 7 and the 5. It's interesting. So because when they're parallel, you will drop the equivalence in terms of the resistance. If they're in series, you're going to add them. It's going to get bigger, but it drops when they're in parallel, okay? right? So your voltage will go up. Interesting. So let's continue on. Let's do CDP, a couple examples of CDP. So here we have a current source, it's 3 amps. And we're looking for, as you think about, okay, CDP is based on parallelism, distributing current is what we're interested in here. So what we have is we have 2 parallel streams, but these 2 are separated in series. So the first thing we'll do is recognize, we'll call this one R1, the top one R1, the bottom one R2, and the 15 we'll call R3, is recognize that R1 and R2 are in series. And let's go ahead and get its equivalent. So then we have 2 exact parallel resistances. Again, CDP, we use the formula when we have exactly 2 parallel resistances. This is 3, we need to get 2 there. So they're in series. So its equivalent, right, is the sum. And of course, that's 30, right? So again, technically what you'd have is this 30 amp current source, I sub S, coming into an equivalent, REQ, of 30 ohms. Sorry, that's a mess. REQ, 30 ohms, and then a 15 ohm, which is R3, okay? And again, the current, what's happening here, the IS is distributing into, say, I1, and it's distributing into, we'll say, I3, okay? So by KCL, we know that the sum of those 2 better be 3, right? So we already know for KCL, they better sum to 3, whatever they are, okay? So CDP is applicable because we have the 2 parallel resistances. And what we know is I1, again, the denominator term is the sum of the 2 resistances, 15 and 30, because we're using the equivalent now. The I3 will be, again, a proportion of IS. This is, again, the proportion of the current that we're splitting. And remember, what we do in CDP is you use your neighbor, the resistance of your neighbor. So the 15 goes there and the 30 goes there, okay, right? So this will give us 15 over 45, which is a third, times the 3 amps. So you'll get 1 amp there. And then over here, you'll get 90. You're going to get, well, you're going to get 30 over 45, right? Times 3 amps. And that's going to give you 2 amps, okay? So the split is 2 amps will go this direction and 1 amp will go this direction, okay? Again, to rationalize that, the equivalent here was twice the ohmage that this was. So the higher the resistance, the lower the current, okay? It's just the opposite of voltage, right? So you're going to get a lower current here because you got higher resistance there, okay? Finally, let's flip it over, last problem in the section, example 20. Now this one, we stare at that and go, okay, everything's in parallel, right? But this is just a reminder, take 2 things at a time. Take 2 things at a time. So again, 3 amps is what we're distributing. Let's call the first resistance R1. Notice they're all the same, okay? And you may be able to determine immediately what should happen without even thinking, because KCL, just so we could argue, from KCL, I sub S would have to be the sum of all of those, right? And then you might argue that, well, the fact that the resistances are the same, those currents are going to all be the same. So automatically the answer should be they're all 1 amp, right? I'll say it again. All the resistances are the same. What's causing the different currents that we're getting from CDP is because of the different proportions, but the proportions are all going to be the same now, right? But just for the sake of the argument, let's just go ahead and do a normal analysis here and say that, well, R2 and R3 are in parallel, right? So the equivalent, let's call it REQ1, the R2 times R3 over the sum. It's going to give us what, 100 over 20, 5 ohms. Okay. Redrawing, the current source of 3 amps is being distributed across a 10 ohm resistance we called R1. And now you have an equivalent, which we're calling REQ1 of 5 ohms. Okay, right? So now we have the perfect situation here. You have two, we've reduced 3 to 2 parallel resistance. We can apply CDP. Okay, and we call this current I1 and this current, so we have to be careful here, right? So this equivalent is not represented by either, and we don't know which current we're trying to get the currents through each of those. So technically we can't just say this is I2 or I3, right? Can't do that. We know the voltages are the same, but we can't do that with a current, okay? So right now, all we can do is get I1 from CDP. So let's do that. So from CDP, we can get I1. Again, let me just back up to make sure that was clear. You can't say this is I2 or I3 because current is not shared across parallel resistances, only voltages, okay, all right? So we can use CDP to get I1. You would use its neighbor, which is 5 ohms, over the sum, which is 10 plus 5, times the source current. And so that would give us a third times the 3 amps, and we get 1 amp, which we know we're supposed to get anyway, right? So we would know by that argument that the I1 right here has to be 1 amp, okay? Right? So if we wanted to find I3, for example, we could use the fact that R1 and R2 are in parallel, right? And get another equivalent and use CDP. So that's the interesting thing here, is we can actually do CDP twice here, because we could have just said, well, you could have combined those two in parallel. So let's do that, just for example. So we could have said a different equivalent, say RE2Q, is formed from the fact that R1 and R2 are in parallel. Okay. And so in that case, the equivalent has to be what? R1 times R2 over their sum. But lo and behold, it's the same values. It's still 100 over 20, which is 5 ohms. So either you have an equivalent of 5 ohms to the left of 10 ohms, or you have it to the right of 10 ohms, okay? So either way, you'll get the same result, that I3 must be the equivalent, its neighbor, 5 over 10 plus 5, times the source current, which is 1/3 times 3 amps, which is 1 amp, okay? I'm not redrawing it, you would just flip it. You'd have the equivalent here for R1 and R2, and this would be R3, okay, sitting over there, right? And then of course, by KCL top node, we must have three has to be the sum. And since 2 of them are each are 1, that would tell us that I2 would have to be 1 amp, okay? Right. Now, you could have argued, someone said, well, you know, you could have done the equivalent with R1 and R3 being in parallel, and then let R2, and the answer to that, and then use that to get the same argument for CDP. And the answer is yes, you could. Yeah, either way. But I wanted you to recognize we kind of know what the answer is, simply because of looking at the fact that the resistances are all the same. So the proportions, my neighbor's proportion is the same as my proportion, okay? So therefore, the currents will all be distributed. The current will be distributed evenly. The minute you change one of these, so that this is like 5 and this becomes 15, right? Everything's different, okay? And then you would just sort of scale like we did here. Combine 2 of them, get 1 of them, combine the other 2, get another one, and then tease out through KCL the third one, right? So those are good examples of what you could expect in trying different reductions to apply VDP and CDP.